All right, Calculus 1, we're in section 3.2. I wanted to do a few more ideas here with you. The power rule. We learned about the power rule, okay? The derivative of x to the n, you bring the n down, you bring the power down, n times x to the n minus 1. So you subtract 1 from the power. Yeah, it's easy. It's real easy here. So when I have a function x to the fifth, this is how we talk. We don't really, it's called y. This is y, f of x. And when I take the derivative, I call it what it is, f prime of x. I try to communicate in a written language called mathematics. Anyway, it's easy. It's 5x to the fourth, right? I'm done. And this is the derivative of this function. This is a function. This is his derivative. All right, let's try this one. Okay, so these next two are interesting. All I have is this power rule. And so I have to be able to write things as powers. That's all I got for now. And so, a square root doesn't look like a power, but it is. So you have to remember some algebra, I'll remind you. But a square root can be written as x to the 1/2 power. So I just rewrote the function. Your book will talk about that. They'll say rewrite the function. Rewrite it as a x to a power, and now you can do the power rule. Here we go, the power rule works. So y prime is, you bring the power down, 1/2 x to the negative 1/2. Did I do that right? Bring the power down, subtract 1 from that. When you subtract 1 from that, you get negative 1/2. So there's the derivative, and that's fine. That's the slope of the tangent line to that function. We often want to rewrite or clean these derivatives up, So here, let's do a couple steps here. When something has a negative exponent, that should be moved into the denominator. So I'm going to leave that 1 in the numerator, the 2's in the denominator. I'm going to move him into the denominator, and then he's x to the 1/2. He was a negative 1/2. I know he's off to the side. Off to the side is up in the numerator, and now he's down in the denominator. I moved him down and changed him to a positive 1/2. That's algebra rules of exponents. Anyway, and then that positive 1/2 could be written as a square root, and that's fine. You may have been taught at times we need to rationalize the square root in the denominator. We really don't need to do that anymore, but it's possible somebody would want to do that. Rationalize, get rid of the square root in the denominator. Like I said, we really don't. In calculus, we learn to be mature. We learn to use our exponents like this. Just for fun, I'd get a square root of x over a 2 times x. That would, actually, maybe you would do that with numbers. I swear, you wouldn't even do that with this problem. Let's not do that. A power rule and a little bit of rules of exponents. Let's try this one. This doesn't really look like a power rule, not quite. It looks like a power in the denominator, but I don't have a rule that says that. I need to be able to move him up and do a power rule. So that's what I do. Again, I rewrite the function using the rules of exponents. I can move that up and call that 4x to the negative 2. That's what that is. Move the x squared up, it's x to the negative 2. That's algebra. Now you can apply the power rule. The derivative is, now we do a derivative. That was rewriting the function. We do a derivative, negative 8 x to the negative 3. Did I do that right? I subtracted 1. Negative 8 x, subtract 1. Negative 2 minus 1 is negative 3. Yeah, and that's it. And that's the slope. There it is. Again, with a negative exponent, maybe you want to rewrite that, clean it up, so to speak. Drop the x to the negative 3 into the denominator, not the 8. The power is on the x, and we drop that into the denominator. So there's the derivative. Cool. Hey, let's do something with one of these derivatives. So that was just an example of using the power rule in certain situations. You got to do some homework and try those different algebraic situations. But I want to do something with the derivative. Let's try this a second. Let's say I am on this function, and let's say I'm at the point when x is 1. So we're on this function, and we're at the point where x is 1. I wonder what the y value is. Well, there's my function. If x is 1, what's the square root of 1? The square root of 1 is 1. Oh, y is 1. could draw a picture of this actually, real quick. This is the square root function. It looks like this. I just tried to observe that I'm at the point 1, 1. When x is 1, y is 1. We're at this point. And maybe we want the slope of the tangent line at that point. Or maybe I want the slope of the curve at that point. Same thing. Slope of the curve is the slope of the tangent line. And do I have a formula for the slope of the tangent line? Aha! That's what the derivative is. That's a formula for the slope of the tangent line. So when x is 1, I can plug a 1 in there, and the derivative is, I plug a 1 in there, the square root of 1 is 1, that's a 1/2, 2's in the denominator, that's a 1/2, and that would be my slope. You know, I don't really call, I mean, that's my slope in general at any x. This is the slope formula. This is for the slope at any x. If I want to know when x is 2, when x is 4, when x is 3, when x is 0, or when x is 0, it's undefined. When x is 1, I can find the slope at any x. So when you give me an x, I can find a specific slope. So now I got the slope of the tangent line, the slope of the graph. Maybe I also want the equation of the tangent line. So here we go. If I have a slope and a point, I use the point slope formula, and I get the equation of the tangent line. That's a typical question. So that would be y minus the y value 1 equals the slope 1/2 times x minus the x value 1. That's my point slope formula. This is the equation of the tangent line. I'm going to write that. Equation of the tangent line. Let's clean it up a little. If I distribute the 1/2, that's 1/2x. Sorry, that's 1/2x minus a 1/2. If I add that 1 over there, I get 1/2x plus a 1/2, I think. That's the equation of the tangent line at this point. The equation of the tangent line to this function at this point. Takes a little work. We use the derivative to get that. We use the derivative to get the slope, and then we did a little algebra. I'll just draw a picture of that. Must cross right there. It's got a slope of 1/2. It's my tangent line. Okay, I'm going to do one more thing before I turn off this video. So we're using this power rule. We see that it can be used in different situations to get the derivative. And it's super basic. I mean, we need the power rule. That's our basic rule. We're going to learn more advanced rules on how to deal with products and quotients and the chain rule. We got a few more things, advanced stuff to learn. But do you want to know why this works? Then you should prove it to yourself. And it won't take me long. Watch. In order to prove it, I want to prove that this derivative of this is this. Why do you bring the n down and subtract 1? I mean, this is how you prove it. If your function is x to the n, and you want to do a derivative, you should do the limit as delta x goes to 0 of x plus delta x plugged into the function, which would be x plus delta x to the n minus x to the n, that's the function itself, all over delta x. That's the old limit definition of a derivative. And if I do this and work this out, this will be the answer, and that'll prove to you why this works. In order to prove to you why this works, you have to know one idea, and I'm going to gloss over this a little bit, but we have to use what's called the binomial theorem. I mean, this is a binomial, x plus delta x, and it's raised to the n power. You know, if it was squared, we would know what to do. If it was cubed, I think we would know what to do. We'd have to FOIL that out, major FOIL. If it was to the 4th, we would have to do a major FOIL. So it's to the n, so I have to do a major FOIL, but the binomial theorem says it'll be this. It'll be that first number, x to the n. Then we'll get an n on there, and we'll drop a power on that to n minus 1, and then it'll be multiplied by a delta x. Then there'll be another coefficient. This n was the coefficient. I'm not sure what that coefficient is, but it'll be x will drop down another power, and then the delta x will be squared. And that'll go all the way out until finally the last term is delta x raised to the n. So if this was completely FOILed out, it'd be this long, long polynomial. and this would be what it looks like. Minus this x to the n, that's this term, all over delta x. And if you remember doing these problems, what would always happen is this x to the n would cancel with this x to the n. What's left is many terms, but they all have a delta x in them. So if you factor the delta x out, you are left with this term, n x to the n minus 1, plus something, I don't know the coefficient, x to the n minus 2, and there's a delta x left on that. There'll be a delta x there, there'll be a delta x there. Way down here, there'll be a delta x to the n minus 1, because we factored 1 out. It's all over delta x. We're trying to take the limit as delta x goes to 0. I bet you remember the next step. After you factor that delta x out, the point was you can't do this limit. You get 0 over 0, but that cancels. Now you can do the limit, and everybody that has a delta x goes to 0. So this next term, whatever it was, goes to 0. This term goes to 0. All these little infinite terms go to 0. That last term goes to 0. And what am I left with? N x to the n minus 1. Pretty cool. That's the derivative. Proven to you with the old long method. All right, I'm glad. You probably just believe it. Just use it. Just believe it. But there it is. Thank you.